My name is Bart Wickel. I'm a conservation hydrologist with the Stockholm Environment Institute in Davis, California. This talk was prepared for the River's Edge West Annual Conference and aims to provide a perspective on climate-adaptive approaches to river restoration under a rapidly changing climate. When talking about climate change, you may have heard the terms mitigation and adaptation. Mitigation aims to slow and eventually stop our post-industrial level emissions of greenhouse gases. And if mitigation works, we will reduce the rate of climate change within the next decades to 100 years. Adaptation is the process of adjusting to and preparing for the impacts of climate change, while we are bringing our emissions down. If adaptation works, we will start reducing our vulnerability to impacts today. It's important to recognize that adaptation without mitigation is not possible. Climate adaptation aims to minimize the risks associated with man-made climate change and primarily focuses on building and maintaining resilience. Adaptation can be seen as buying time while we stabilize and reduce our emissions. People and nature have been adapting to changing climate conditions for millennia and beyond. So some will say, what's different? Well, the current rate of change that we're experiencing today is much more extreme and faster than we've observed in the past hundreds to thousands of years. In addition, it's very important to acknowledge that, especially in the past century, the world has also dramatically changed, resulting in the loss of habitat, connectivity, species, and we've over-allocated water resources. And therewith, we've dramatically reduced the ability to adapt. As pointed out by Millie in 2008, many of our approaches to water management are founded on an assumption of stationarity. When we designed our water management infrastructure, such as dams, irrigation districts, flood control structures, we have generally used observations of the past to prepare for future conditions. This has resulted in the fact that many of our policies, institutions, and infrastructure design and conservation approaches are fundamentally flawed in their ability to adjust to emerging conditions. One of the most common examples is the exposure of coastal communities. Approximately 40% of the global population lives within an area with rising sea levels. While countries like the Netherlands, where I'm from, have shown that it's possible to adjust to these conditions, it needs to be acknowledged that there are hard limits in our ability to engineer ourselves out of these problems, primarily due to costs, but also technical limitations. A great example of a piece of infrastructure that was designed with a mismatched hydrologic reality is the Hoover Dam. As some of you may know, the Hoover Dam was engineered based on approximately 30 years of hydrologic observations, which in retrospect turned out to be the wettest decades in Colorado River Basin history. Once such a piece of infrastructure is in our landscape, we have significantly reduced our ability to adjust to other conditions. And both from an engineering and environmental perspective, you end up with a maladapted situation. When we look at the past 100 years of change in, for example, temperature in the top left map, we see a clear pattern of strong warming and some moderate areas of cooling around the globe. For precipitation, however, the top right map, this average signal is nowhere near as consistent and much less predictable. The same goes for projections based on state-of-the-art climate models, which indicate a strong consistency in trajectory towards continued global warming, as represented in the figure on the bottom left. For precipitation, however, there is a broad scattering of projections and no consistent global or regional direction for emerging patterns and conditions. When discussing climate change, there's a strong emphasis on global warming, changes in temperature. A lot of the changes that we may experience or are experiencing already actually come to us through changes in the hydrological balance. We get more extreme events such as floods and hurricanes. There are shifts in seasonal onsets of spring burst, changes in snow and ice melt, and the duration of dry seasons. And we are already experiencing system level shifts in fire regimes and systems moving from perennial to intermittent flows. When we discuss climate change, change is often presented as a change in average global conditions. By 2050, for example, we'll have a 2-degree increase. But the reality is that the changes in our climate come to us in a variety of changes. We have changes in extreme events. We have shifts in seasonal and annual dynamics. And we can even have state level or system level shifts. And so when we're designing our climate adaptation options and are evaluating the impacts of climate change on our conservation efforts, it can be helpful to conceptualize the different kinds of changes that might take place and how they affect our objectives. In extreme events, we expect both the intensity and duration of events to increase and the return periods to shorten. We already see this with the fire regimes, for example, in California, where the return period has dramatically shortened and fires have become much more extreme. Seasonal shifts are reported widely throughout the world. In the Northern Hemisphere and especially in the United States, we already see shifts in onsets of spring, earlier springs. We see stronger, deeper polar vortices and longer dry periods and a greater frequency of heat waves. In some parts of the country, we see shifts. For example, in California on the West Coast, we see fire-adapted forests shift towards grass-dominated ecosystems, resulting in Arizonification of our ecosystems here. In places like Oregon and Germany, wine industries are booming, while southern industries are struggling. To a cascade of impacts due to changing flow regimes, which in turn affect sediment balances and eventually habitat structures. When we are designing river ecosystem conservation strategies, it's therefore logical to evaluate this interdependency. This cascade of impacts is what's already being observed in terms of geomorphologic change, for example in the Escalante river system, as shown by Mike Scott in the previous presentation. A qualitative approach towards adaptation is a thought framework that lets planners, decision makers, and practitioners evaluate the broad range of uncertainty that is inherent in natural science and climate-related work. One could, through a set of guided questions, evaluate the state of our current knowledge, but also evaluate less likely events and how one would potentially prepare for those, and possibly design low-risk pathways that aim to embrace uncertainty rather than ignore it. Adaptation in many cases may end up resulting in very similar actions to the ones that we're employing now, but the most important difference is that we're deliberately exploring the potential impacts of climate change and are monitoring for the indications of change that help us adjust our actions more dynamically. When designing climate adaptive conservation strategies, we can employ a variety of qualitative approaches. When preparing for extreme events, one can consider historic events and evaluate where our responses failed in the past. And consequently, we could aim to do better. Some climate disturbance events related to, for example, El Niño, are more predictable and can be used as a proxy when thinking about adaptation strategies. Imagine, for example, what happened during the last El Niño event and prepare for those events to be more frequent and more intense. And think about how we would change our strategies based on that knowledge. In the context of Rio Grande Basin conservation, we started integrating climate proxies, which means we were looking at places, for example in northern Mexico, as a proxy for future conditions in Texas. Through temporal proxies, as a way to develop climate adaptation, we looked at recent severe droughts as a means to understanding how future drier, warmer conditions might affect natural processes in the watersheds that we work. Understanding tipping points is arguably one of the most important aspects in climate adaptation, which allows us to determine both the direction of change and a potential point at which certain strategies don't make sense anymore. Rather than pushing a boulder back uphill, we could find ways to facilitate change and adjust accordingly. Lastly, monitoring is becoming increasingly important to understand the changes taking place and to evaluate the effectiveness of our chosen approaches. The case of the restoration of silvery minnow in the Rio Grande provides some surprising ideas for potential adaptation strategies. Silvery minnow has experienced a dramatic reduction in its original range due to damming and over-extraction of water for agriculture and industry over the past decades. The species has been experiencing increasing climate pressures over the past decades as well, through longer low flow conditions and changes in water quality. For many years, Fish and Wildlife agencies have attempted to release and reintroduce silvery minnows in the Rio Grande, often causing conflict with farmers. A few years ago, biologists discovered that one of the reasons that the reintroduced minnows are surviving dry periods turns out to be the fact that they can enter irrigation canals through screens, while larger predatory fish are screened out. Deeper ponds in the irrigation system allow the fish to survive and come back once the river flows are back up. So with these surprising new kinds of refugia, we may be able to design and engineer better solutions for these fish than we are doing right now. This also shows that there might be synergistic benefits, and sometimes small modifications in management practices may have big impacts. So looking at adaptation measures in this kind of context, what would they look like? Well, we could map refugia and put stronger emphasis on the conservation of refugia, springs and seeps, along with adjustments in flow management. We should, however, also explore at which point we may have to give up on conserving this kind of species. The case of the Escalante River, shown in the previous presentation by Michael Scott, is facing challenges with the expansion of invasive Russian olive. Current efforts focus on eradication and the planting of native species. Adaptive strategies in this context might emphasize the importance of tipping points and understanding when we won't be able to go back to a system without the presence of this invasive species. We could also explore synergies in adaptation efforts by focusing on restoration of reaches that would benefit fish species as well as other conservation targets. When approaching eradication efforts, we could imagine taking a general upstream-downstream connectivity into account and design an approach that would work from the headwaters towards the outlet to prevent receding and managing flows to prevent kinds of events that trigger the recruitment of new reaches by Russian olive. While this is by no means a comprehensive review of all aspects of climate adaptation, I hope that this brief overview provided some guiding adaptation principles and help you in designing future adaptation projects. The role of tipping points in the exploration of novel and sometimes unusual synergies might be more important than is currently thought, and could help identify climate change as a new opportunity for collaboration rather than an area of conflict. Thank you for your attention.